Hi there, this video is brought to you by the Math and Science Learning Center as part of the Quantitative Literacy and Reasoning Lecture Series. This particular video will cover exponential functions. Functions in general have many representations, and one of those that helps us understand their characteristics and relationships between values is an x and y chart. So here we have an x and y chart. You've probably used these before with linear functions to understand that they have a constant rate of change. Right, but with exponential functions, we have a little bit of a different relationship. So in this particular chart, you'll notice that our x's are increasing consistently, right, with 1 unit each time. But our y values have a little something different going on. The first time it increases by 4, the second time by 6, the third time by 9, and so we really can't see an immediate pattern. However, if we take the ratio between our values, our y values, so if I do 12 divided by 8, I find that the ratio between them is 1.5. Okay. And if I try that again with 18 and 12, I'll find 1.5 as my ratio again, meaning that if I were to multiply 12 by 1.5, I would get 18. And similarly with 27 and 18, I have a relationship of 1.5. I could also say that 27 is 150% of 18. So we have this nice relationship here where it's increasing by the same percentage each time, right, of 150%. That is the hallmark characteristic of our exponential functions. Though they don't have a constant slope, they do have a constant percent change. So we can represent this relationship algebraically as well, in multiple different ways. Our most generalized form is f of x equals a times b to the x. With exponential functions, we always see that the exponent is a variable, here represented by the x. So a is something that we fill in. It's our initial value that we're given. In the last example that we saw, our first value was 8, right? X was 0, and the y value associated was 8. Our growth/decay factor is however much the percentages that it's growing by each time. So in the last example, we saw that the ratio between values was 150% or 1.5. And then we leave our x there to be filled in by some sort of value. Okay, one thing to note is that b is always going to be greater than 0. So if b is greater than 1, we call that a situation where there is growth. Yeah, just like in our example we just saw where our value was 1.5. If we looked at the graph for that, x and y, we would see that our chart looks a little something like this. Yeah, it grows very rapidly but at a consistent percent. If our b is less than 1, which means that it's a fraction, we call that a situation of decay or decrease, right? So our chart will look a little something like this, where it is decreasing very rapidly. We can also represent our exponential functions with this middle value or middle equation, right? This version is going to be very helpful for us in our types of problems that we'll see. So P naught is how we say that, and that's our initial value, just like our A in the previous situation. So R represents the amount that we are adding on to what we already have in terms of percentages. So if we look at our previous example, we were taking 50% extra each time. One thing to note about R is that it's always going to be a decimal value and not a percentage. So when you write it in your formula, make sure that you're actually writing it as a decimal. And then t is the value of time periods that have occurred. Our last version of exponential functions is this final one where we use a value called e. Even though it doesn't look like it, it is a number itself. We won't really cover that too much in this video, but You will see it in the future when you're talking about anything with continuous decay or growth. So let's try this out with an example. So we are told in the year 2020, the world population is approximately 7.78 billion people, and it's growing at a rate of 1.08% per year. If this growth rate continues, we want to know what the population is going to be in 2023. So anytime we deal with a problem, our first goal should be to identify what information we have and what we're trying to find. So I know that my starting value is 7.78 billion people, and it's growing at a rate of 1.08% per year. I also know that I'm looking for the population in 2023. Yeah, so if I think back to that middle version of the exponential function, I already have P naught, right, as 7.78, because it's my initial value of people. I know that it's growing at a rate of 1.08% each year, but I know that I don't want to write it as a percentage. I need to write it as a decimal. So I'm going to move that over by 2 places and get 0.0108. And then lastly, we're told that we're looking for the population in 2023, so that means it's going to be 3 years from our starting place of 2020. So now I have all of the information I need. I'm looking for P of 3. Okay, so I can fill in all of my spaces with the information I've been given. Do make sure that you add everything with add or subtract in certain cases, everything that's in the parentheses first before applying the exponent. And then from there you can plug it in your calculator, and you should find that there will be 8.035 billion people in the year 2023, assuming we stay with a consistent growth rate. And we can generalize this if we leave the t open. We see that we have this chart. It looks very linear, but that's only because it's not growing by a very high percentage each year. So let's try one more example to make sure that we have a good handle on this. So at a track and field tournament, a quarter of the participants are eliminated each round. There are 256 athletes in the tournament, and we're looking to see how many will be remaining after 4 rounds. So if it's not immediately clear that this is an exponential problem, because you don't see any percentages hanging around, something to keep in mind is that we're not going to be eliminating the same amount of participants each time, right? We can't just eliminate 5 or 10 or however many, right? It's going to be changing based on how many total we have at a current moment. So we're dealing with percentages even though we don't immediately see them in our information that's been given to us. So just reminding ourselves of the exponential function, right? Our first piece of information that we're given is that there are 256 athletes in the tournament as a whole, right? Which is going to be our P naught. Our R is a little bit hidden though. We are told that a quarter of the participants are eliminated each time. So when you think of a quarter, if I'm representing that as a percentage, I'm thinking about that as 25% of the participants each round are going to be gone. Now, if they're being eliminated, I want to think of that as a negative value. So if I'm going to write that for my R as a decimal, I want to write negative 0.25. And then lastly, we care about the value after 4 rounds, so t is going to be equal to 4. Great, so now that we have all of our information, we can plug it all in, making sure we do 1 minus 0.25 and raise all of that to the 4th. As before, make sure that you do everything in the parentheses first, and then raise it to the 4th power, and you'll find that you have 81 contestants left after the 4th round. Again, we can generalize this and see our chart. This one looks a lot more like what we would expect from an exponential function because it's decreasing at a pretty quick rate. You can also see that the tournament will end somewhere between the 15th and 20th rounds, because it gets so low that we've found the top contestants. Right, so hopefully this has given you a better understanding of exponential functions as a whole. If you have any more questions about this topic, feel free to reach out to the Math and Science Learning Center, and a tutor will be able to help you there.